Okay, so how do we measure speed, kids? That's what we're going to be talking about with this right here. Again, I'm going back to this graph that we've kind of discussed already. We talked about this. There's a constant rate of change or a constant slope on the purple line from point to point that's listed up here, but on the red line, is that slope constant or is that changing? It's a changing slope. Okay, it starts out kind of flat and then increases. And when we talk about what we're going to deal with today in terms of how do we measure speed, the first thing we want to know is how does using, I'm going to underline a phrase right here. I think you should do the same thing. How does using, what are the next two words? How does using average velocities help us understand what, kids? Instantaneous velocity. Where are my track kids at? All right, Lake, let's talk. Lake, when you start a race, which race are we going to talk about? You want to talk 32, 16, and 8? What do you want to talk about?
16.
Let's talk about 1600. Do you ever find yourself in a 1600 trying to pace yourself at all?
Yeah.
How about your pace at the very beginning of the race? Is that pace faster than maybe the middle part of the race, or is it the same?
It's faster.
So you're saying your pace at the very beginning, your velocity at the very beginning of a 1600 is faster than that when you settle into the race. Is that true?
Yep.
Okay. So I had to ask you this question. Do your velocities stay constant throughout that race, or do they vary, or do they change a little bit?
They change a
They
little bit.
change. Sometimes you want to accelerate, or sometimes you accelerate quick, you get out, and you have a high velocity to start to establish, and then you settle into the race and move back and down a little bit. What typically happens at the end of that race to your velocity?
Kick it in high gear.
You're going again. So we're going to talk about it. Lake, if you ran a mile in what? 4 minutes and 36 seconds?
10 seconds.
4:10? That's what you're going for now? Okay. What is your best? 4:26? Okay. That's impressive, by the way. But could I say that throughout that race, Lake averaged a certain speed by saying it took him 4 minutes and 26 seconds to run a mile?
Say I wanted to get a 5-minute flat mile, it'd be 115, 115, 115.
Okay. So whatever that would turn out to be in miles per hour, I don't know what that's going to be. If you did it in 5 minutes, it'd probably be 12 miles per hour. Okay. So did you run that? Let's just say you ran a 5-minute mile. Would it take you? Would you be going 12 miles per hour the whole time?
No.
You're going different speeds, right? Okay. So we would say the average velocity for that whole race might have been 12 miles per hour, but that doesn't mean you were going 12 miles per hour at every single time
So
throughout
is
the
that what
race.
we're trying to do for the graphs?
Kind of what we're going to start talking about is how fast were you going at minute 1, and how fast were you going at minute 2, and how fast were you going at minute 3, okay? So when we talk about average velocities right here, kids, this is going to be like, how long did it take you to run the whole race? What was your average speed for the whole race, okay? And that's going to differ from instantaneous velocity in that we're going to look at a specific time. How fast was Lake going at 2 minutes and 33 seconds, okay? And we're going to look at graphs to try and figure that out. Now, what was the one key word I asked you guys to remember as we go through this section to start today? Okay, average velocity is a biggie, but we had all these formulas over here. What did I say? They're kind of like a what?
Slope.
Think slopes. Okay? There's going to be two types of slopes that we look at graphically today. And one of those slopes is going to give you an average velocity, but another slope is also going to give you an instantaneous velocity. And we'll talk about what instantaneous velocity is in a little bit, but really, if you can understand that average velocity is like over the whole race, and an instantaneous velocity is a velocity at a certain time, I think you'll understand what's going on here, okay? So goals today. First thing we want to do, volunteer to read this one.
Evaluate average velocity on a given.
Okay, so we're going to look at velocity over a given interval. We're also going to use this idea of limits to gain an understanding of instantaneous velocity. How many of you have heard of instantaneous velocity before? Have you talked about anything being instantaneous in science classes ever? Think so? Okay. We're going to understand a limit as x approaches a constant value of c. I'll show you what this means. And then we're going to use some algebra to determine some limits today. So I kind of tell you what this is all about here, all right? I want to go back to that graph here in a little bit, but first things first, let's get some formulas written down here, okay? First one we have there is average velocity. Do I have a volunteer that would read that for me?
If S of t is the position of an object at a time t, then the average velocity of the object over
Okay, and I'm just going to say that this is really your slope, okay? Here's the formula you're going to need. The average velocity is going to be S of B, okay, minus S of A, all over B minus A, all right? Guys, what kind of a formula does that kind of look like from what you've had in past math classes? Looks kind of like this slope formula up here, this y2 minus y1 over x2 minus x1. That's kind of what we're talking about. We're saying, well, what was your position at time B? What was your position at time A? And how much time did it take you to run that? We'll show you some examples of that, but that's what you need to know, okay? Then, the instantaneous velocity of an object at time t equal a is given by the limit of the average velocity over an interval as the interval shrinks to be around what value? A, all right? I want to make sure I got the proper formula for you on this here. They use some different variables of time, so I want to make sure we use what we need to. But right in here, this is how you write instantaneous velocity, okay? Now, again, instantaneous velocity is that velocity over a whole period of time or at one certain time. If I want to write this down, it's velocity at one time. Okay. Now here's a formula you're going to hear me talk about a lot. Okay. This is going to be the limit as we say h approaches 0. Okay. We're saying we're going to look at one specific time, and at one specific time, we're only going to look at that time frame as something really close to 0 seconds changing. We'll show you here on the graphs what we're actually looking at. But it's going to look like this. It's going to be S of A plus H minus S of A all over H, keeping in mind that H is really, really close to what, kids? 0. It's going to approach 0. It's just never going to get there, okay? Guys, the way I wrote this, would I ever want H to equal 0? No, okay? So I'll show you what that instantaneous formula looks like here graphically in a little bit, but just have that down for now, all right? And then the last term we need to make sure we understand is limit. And it says in mathematics, a limit is the value that a function or sequence approaches as the input approaches some value. So maybe I would say this. An example might look like this. I might say, what's the limit of this function as maybe x approaches 2 for, I don't know, how about x plus 6 over x minus 2, all right? So just have that written down. We'll come back and talk about that right there, but where would you have a vertical asymptote at, guys? 2, wouldn't you? Okay. Forward here again. I was back to this idea of limits, kids. Why did I say the limit as x would approach 2 here? Does 2 offer any problems here at all?
Yeah, because 0, it'll be 0.
So the denominator would be 0 when x is 2. So this would be discontinuous at 2. And what we talk about with limits is kind of like this. And I'm not going to draw it on the board up here with a smartboard. But sometimes we have graphs that do this, kids. They'll go up. There'll be a spot right here. And then go back down like that. And we say that this graph is discontinuous here, but we want to know what value is that discontinuity. So we say, well, when you get really, really close to that point that's not there or undefined or something like this, we might say, well, the limit value is maybe 6, okay? And we'll talk more about what that looks like, but
What's the trick for finding horizontal asymptotes again?
typically 0 is in the denominator. For horizontal asymptotes, you would look at your highest degrees here. So where would this have a horizontal asymptote?
0?
Well, what's 1x divided by 1x going to be? Okay, so 1. But again, do you understand why the limit of x approaches 2 is here for this function? Because 2 would make this what value in the denominator? 0. And we'll look at examples. You'll understand that. But just understand that when we talk limits, this is going to be the type of format that you're going to see for this type of stuff, okay? So average velocity, instantaneous velocity, limit, those are the biggies today. Some explanations over here. Questions about the vocab before we start moving on to examples? Let's talk. First thing, example 1 says use tables and what? Decimals, okay? I'm going to put decimals up here, but what I need your help with here, kids, is help me just getting this table entered in. So You guys just have your table there. We'll read the graph here. I'm going to form a table up here. All right, so I'm going to go plus, add a table. Okay, what's the first point we have there, kids?
0, 10.
0, 10.
145.
145.
270. 3.
385.
85.
All right.
490.
585.
585. Does it start mirroring now?
Is that first?
And then 670.
Okay, so I'm going to get these points plotted so we can see them. Okay, so this is kind of what we get right here, kids. You all right with that? For points. So, right here, kids, this is really what they're going to say. Anytime they ask you about average velocity, what's the question say on example number 1?
Compute the average velocity.
Okay, so do you guys agree the y values, is the y the number of feet that it is in the air, kids? And then x is the number, is it seconds or minutes?
Seconds.
Number of seconds. So at time 0, how far in the air is it? 10 feet. It gets all the way up here to a maximum of how many feet?
90.
At what time?
4 seconds.
Okay, and then it starts to come back down. So guys, talk to me about the slope to begin with. Is the slope positive or negative to begin with? Positive until it gets to the very top, and then what happens to your slope here then? Okay, so let's talk about this. It asks about average velocity, and if we're talking about the y-axis right here being something that's measured in feet, and the x-axis in terms of seconds, the rise in feet over the run in seconds is going to produce a slope where the unit is feet per what? Feet per second. I mean, isn't feet per second going to be some kind of a velocity unit? It is, isn't it? So when they say this right here, what's the average velocity on these types of graphs? I'm just going to tell you, kids. It's simply the slope. It's simply the slope between the 2 points. If they ever ask for average velocity, it's just the slope between the 2 points that they're talking about. So what t-values are they talking about here, kids? Time 1 to time what? Okay, so at time 1, what was the height at time 1? And what was the height at time 3? Okay, so here's how you would find this average velocity. I'm going to call it average velocity would equal, okay, it's basically your slope, all right? So it's like your 85 minus 45, or I'm going to write it maybe this way. It's really f of 3 minus f of 1 all over 3 minus 1, okay? Don't you agree that f of 3 and f of 1 are like a change in y values here, or a change in our height, if you will? Okay, what is f of 3, kids? So this becomes 85 minus what? And then how about on the bottom? 2. Well, what is 85 minus 45 up top? Okay, let's talk about this. It simply says at time 1, the height was 45 feet. At time 3, it was 85 feet. So what's the displacement in feet? Well, from 45 to 85. 40 feet up, isn't it? Okay, over how much time did it take to rise 40 feet? Now, did it rise at a constant rate, or was there some curve to that graph? Okay, so we would say that the average rate then would equal 20 feet per second. So in that interval, from 1 second to 3 seconds, what was the average velocity of that object that was thrown in the air? Average 20 feet per second. Does that mean it was going 20 feet per second all the time? No, it just simply means in that time frame, kind of like Blake's race, over the whole interval, that's what the average speed turned out to be, 20 feet per second. Okay? So let's flip the page on this thing. All right? Again, think about something being thrown up in the air here. So it says, for example 1, compute the average velocity over the interval 4 and 5. Okay? What's the significance of the sign here? Well, let's go back to 4 and 5. We would really want to evaluate for average velocity here, f of 5 minus f of 4 all over 5 minus 4. Kids, what value was f of 5 on that table? 85. What was f of 4? And then 5 minus 4 in the bottom is what? So we end up with negative 5 over 1, which is what value? So it's traveling negative 5 feet per second. Now kids, on the interval from 1 to 3, we were at positive 20 feet per second, but now all of a sudden we have a negative velocity. So what's the significance of a sign when we have something being thrown up in the air? What's that telling you? Say that louder, Daddy. Either going up, and that negative sign indicates that it's on its way back down. You bet. Okay, and we can confirm this, guys. 4 and 5, time 4 and time 5 right here. Isn't that what we have kind of right here? Time 4 and time 5. Okay.
So how can you find when it's at 0 velocity?
Well, 0 velocity was positive, got to its highest point, and then did what?
Started going down. So
Sorry.
I know where the 0 is by looking at it on a graph, but can I find that mathematically?
We will. Just not today, but we're going to. That's a huge focal point in calculus.
Will you always use the right number in the interval?
You always want to pick the right-hand interval first and then the left-hand value second on that, yes. Okay. But if you didn't, here's the deal. If you didn't, this would be another way to think about it. If I did f of 4 minus f of 5, as long as I went the same order down here, 4 minus 5, you'd still get the same thing.
Oh,
Awesome.
okay.
You okay with that?
Yeah.
Okay. So what's the negative sign indicate? This negative sign indicates that it is going up or falling down. Yeah, it's returning to the ground, right? It's returning to the ground. Okay. You guys good with that? Average velocity. If I say find the average velocity, you're simply finding what between 2 points?
So,
You're just going to look for the slope and then attaching proper units. In this case, feet per second. All right. Okay. This next one's kind of a biggie. I think example 2 is important because we need to understand how to visualize instantaneous velocity. Okay. So, can I give you something for instantaneous velocity that I think you should remember? Okay. I'm going to write this down. You guys know what a tangent slope is? Do you know what a tangent line is? Say it again. Sine over cosine. That's one definition of it. Unfortunately, probably not the one we're looking for. All right. Here's what I'm going to tell you. Here is a curve. All right, you got that curve like this? And then here is a little point. That little point's right about there. And ready for this?
No.
There, my friends, is a tangent line.
I'm just scratching away. There's no reason. You can stop judging me, Molly.
Why is that a tangent line?
Just judge me.
First of all, does it intersect the graph? Does it intersect the graph at multiple points or just at one point? And here's the deal. This is exactly what instantaneous velocity means. Instantaneous velocity means what's the slope of a tangent line just at that point? So my question is this. I don't have 2 points to determine a slope between here, but if you can imagine this interval getting really, 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 really small around this point, This would kind of be the slope right here. We would say that's the instantaneous rate of change right there at that point. Okay? So, can you visualize tangent lines at certain points, first of all? Okay, so let's talk about this right here. There's a difference between average velocity and a difference between instantaneous velocity. And right here, let me blow this up a little bit. This says on this graph down here at the bottom, it says, the graph of P of t in the following figure gives the position of a particle P at what? It says, list the following quantities in order, smallest to largest, with 1 representing the smallest value. So here's the deal. First thing it says is the average velocity from what to what? Well, let's kind of identify where f of 1, or I guess I'd say in this case, where p of 1 and p of 3 might be. Do you guys agree that 3 is going to be right in the middle here pretty much? Maybe closer to 5. This is 0, right? So won't 3 be right about here, kids? And 1 be right about here? So won't p of 1 be right about there? And won't p of 3 lie right about here? Okay, so if this is p of 1, and this is p of 3, guys, talk to me about that path. When I start on that path, talk to me about the slope. Does the slope start out little and get steeper? Does it get steeper and then become less? What's going on here? Getting bigger, isn't it? Okay. So think about this. I'm just going to try and sketch these in here as best I can. I'm not going to ask you to do this. Maybe this will help you if you see it this way. I'll do my best, all right? Maybe this is my slope for that line at, gosh, that's pretty good. I think, give me a second, let me extend this way. Okay, you guys agree that that'd be like a tangent line to that point right there? All right, let me get a different color up here. Yes. How about this? No, I didn't want to do that. How about this slope right here?
Where they intersect, does that mean anything?
Not really. But guys, which slope appears to be, I don't like this color here. I don't like that. I want that to be like that. Which one appears to be the steeper slope? Kind of the purplish line or the red line? Okay, so if this started out steeper and then gets flatter, what's going to be true about the average if it's really steep here and this is less steep here? The average between the two kind of be between them, isn't it?
Yeah.
Because if the slope of at 1 is like 10 and the slope of at 3 is 5, then wouldn't the average be
7.
7.5, right? So which one of these is the smallest slope? P1, P3, or the average? P3, okay? The slope, anytime they ask about instantaneous velocity, kind of look at the slope. Is the slope steeper here or less steep here? So which one's the least value here, average velocity? 1 to 3, instantaneous 1 or instantaneous 3? Okay, then what has to be the next? Okay, and it's kind of hard to see on this graph. They'll give you a better graph where you'll see that. But the average would be second, and then the instantaneous velocity at 1 was most. And think about it, kids. If I throw something up in the air, well, what's working against it after I throw it up in the air?
Gravity.
So as I throw it up in the air, right at the beginning it's fast, but as it starts moving up and up and up, what happens to its velocity? It starts to slow down, doesn't it? Right? All right. So let me ask this question. This is what I'm really after here. Do you understand the difference between average velocity that we looked at on the previous example and how that compares to instantaneous velocity now? In the instantaneous velocity, I want you to think what? Tangent slope, okay? And do we all understand what tangent line means at a point? Happy with that? Okay, let's move on. Let's see what else is in here. Oh, I love this stuff. This is so much fun to me. Sorry, if that makes me weird, I apologize. Ooh, I like this one. Uh-huh, uh-huh. Okay, then never mind. Evaluating what, kids?
Limits.
Limits. This is where things get so cool, okay? It says for any real number r, let mr be the slope of the graph of the function for y equals what? All right. It says estimate what? To what? We need to estimate. What's the slope of this? What this is really saying is give me an estimate on the slope. Now, guys, I'm going to show you something. This is so cool. All right? You guys don't share that enthusiasm?
This is so cool.
It is. All right, let's do this, kids. Let's get a visual of this first. So, you guys tell me, I'm going to get rid of this table. You tell me, what's the function again?
This chapter.
Was it 2.3 to the, oops. Was it 2.3 to the x, kids?
Yes.
There's our graph, okay? Now, we're really concerned about the slope.
Mr. Carson,
Yeah,
hey, could you say Maddie Fresh, Aubrey Schmidt, and Maddie Bonner to Mr. Tunks's office?
to where?
The office.
Okay.
Thanks.
What'd you guys do? You're gonna tell me, aren't you?
Yeah, if we come back.
Hey, if it's about me, hey, if they're asking about me, you guys have my back, right?
Yeah, we got
Oh, okay, okay.
Is it Mr. Flushing's office? Are we gonna do anything with like initial velocity? And
Oh yeah. Yep, it's all coming.
Yes.
What value are we concerned about the slope at?
4 and 5, right?
Okay, here's what I need someone to do. You see this function up here, 2.3 to the x?
Yeah.
Who has their calculator handy for me? Type in 2.3 to the fourth power and give me that exact value. 2.3 to the fourth power.
27.9841.
27.9841.
Yep.
Okay, now guys, take a look at this. We are looking for a slope of a line right here. We're looking for the slope right at that point. That makes sense to you?
Yeah.
Now I'm going to key in on this point, kids. Here's why I'm going to key in on this point. I'm going to start zooming in on this point. Watch what happens. See how it's curved right there? The line's pretty what?
Mediocre.
It's pretty curved right there though, right? Watch, just kind of keep an eye on the graph around that point. If I start zooming in on that point right there, what starts to happen to the slope of my curve the more I zoom in?
Straighter.
Starting to get straighter
And straighter.
and straighter
And straighter.
and straighter.
And
Oh my gosh.
straighter.
So here's the deal. If I could zoom in on this point, couldn't I almost find the slope between the point that we're at and say a point really close to it to get an idea of what the instantaneous rate of change would be? Is that okay with you guys?
No, it's cheating.
It's almost cheating. I'm going to zoom in one more time. What the heck?
Do it again.
Whoa.
2 more times. 2 more
Two
times.
more times? Okay. We're zooming in so many times that our distance from 4 to this point right here is really close to what value? What's the distance from 4 to 4.01?
0.1.
We're looking at a slope over a very, 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 very small interval, right? Or in other words, our distance or our change there, our limit is starting to approach what value?
0.
That's where that stuff comes from. So let's do this, kids. We've got this point, don't we? Okay, I'm going to put a point up here. I'm going to put a point up here that's really close to it. How about right? Let's pick this one. Somebody remember that coordinate. 4.001 comma 28 James Bond, right?
Wait.
28007. 28 James Bond, right? Oh, come on, that was good. You're supposed to laugh. Good God.
Did you do this on purpose?
I love it.
You know, make another one.
What was the point? 4.001 comma 28 James Bond.
Judging people.
Hey, is that point on the line?
Yeah.
Maybe.
What are you laughing about?
They're judging people that are going to out of state.
I took a picture on your Chromebook and my head was like,
Oh, oblong. Did your face have an instantaneous rate of change on that?
probably.
Yeah, okay. Let's find the slope here, kids. Help me out. I'm going to go 28.007 minus what?
27.9841.
All over 4.001 minus 4. All right, help me with the math up top here, guys. I don't... Ooh, 159 and 7. Is this 0.166? No. 5.9. Somebody just do it.
Last number's going to be 6.
Mm-mm.
The number before that's going to be
Last
5.
number is going to be 9.
Oh, yeah. Wait. What?
0.0229 over what, kids? Point. So, right? So the slope would be about how much here? Rate of change at that point is about 22.9. Okay?
How do you do that? Why did you move the decimal places?
Because this divided by this, since there's a 1 down here, if I move the digits 3 to the right, that becomes a 1 down here. That would become 22.9 divided by 1. But
cheating.
no, this is just being efficient.
This is cheating.
Okay, so what's a good estimate for the slope there based on what we had? Okay. Thing I'm trying to point out to you is this. When I'm trying to approximate not an average rate of change, but an instantaneous rate of change, we're still looking at slopes, but am I looking at slopes over a big interval or something infinitely small? What did we do with this point right here? Did we zoom out or zoom in? We kept zooming in, and we looked at not the whole part of the graph, but we looked at a very, 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 very small part of the graph. Guys, was my change in x a lot or a little?
Little.
Okay? We measured 1/1000th of a unit. Am I okay?
Yeah, you're good.
Okay. Measured 1/1000th
Can you do
of
the
a
same?
unit.
Can you do the same thing if you zoom out?
Very nice. Okay? All right. Congratulations. Okay? Now, those of you that left, the rest of the class will explain it to you at some point, all right? So what was a good estimate for slope here, kids? At x equal 4. What was it? What was a good estimate for slope? 22.9 units. Okay? So rise 22.9 units for a run of 1 rate at that point is a great estimate. All right. Well, that being said, where did I set my pen down, kids? Oh, why do I do this to myself? Probably. Good God. Okay, so we're doing well here. Okay. All right. So again, when I'm looking at a slope at just one point, are we looking at a really big window or a really, really small window? Okay, and here's the deal. We knew this point was 4 comma what? And we zoomed in, we said, well, look, from 4 to 4.01, that's not that much distance. Shows up big on the graph. We picked this point right here of, right? Because watch it when I zoom home again. Here's the actual graph at 4. When I zoom home again, at 4 right here again, kids. That point is right about think about it. At x equal 4, this is the original graph. There's that point. Is that slope pretty steep or not? Yeah, pretty steep. Slope of 22.9 there, okay? If I zoom out a little bit again, right at that slope, again guys, it's gonna continue to zoom in on that point. Or I'm zooming out, I should be zooming in, I'm sorry. Curve there a little bit. Keep zooming in, zooming. Keep zooming in on that point right there. What's this line eventually start to look like? Something that's curved or something that's straight? Straight line, okay? And we just pick some points there. We know that this is 4 comma whatever. I picked that other one up here to be 4.01001 comma 28.007. We just found the slope between those 2 points, okay? Again, keep in mind from 4 to 4.001, that's like a limit as our change in x approaches what value? 0, okay? Dividing by 0 down there is kind of what we're after here, but we don't want it to be exactly 0. So that's the idea of a limit there, all right? So what did we get for values up here again? I'll write them down. 28.007 comma, or minus what? 9841. And we got these off in decimals. All over 4.001 minus 4. That equal, what do we get, point? Is that 0229, Sybil?
Did you use that one, the same formula that you used for?
Nope, so this was the graph that they asked us to put in there, right there. That's where that graph came from, okay? And then I asked the kids to say, all right, tell me what 2.3 to the 4th power was. And that was the point 4 comma 27.9841. Okay, so when I had this point 4 comma 27.9841 put on the graph there, Maddie, I said, okay, let's start zooming in on that point because we're going to make a line and tangency to that or something really close to that. So I kept zooming in on it and got a really small window on these values right here to approximate the slope right around that point. Okay, so let me go back to my graph here quickly. There's the graph right there. Curves, right? Okay, and if it's curving like this, is that a straight line? Can I get an exact slope, or would I get an average slope between points? So what I told kids was this. I said, start zooming, find your point that you're at, which we knew was 4 comma, after I put the 4 in, this was the point right here. Okay, we want to know a good idea of slope here. Well, I don't want to pick points kind of around here. I could and get an approximation, but I said, what if we start zooming in on this? And I said, we'll start zooming in on that point right here. We're going to zoom in on that point. Keep zooming, keep zooming, keep zooming. And the kid said, Arson, the more you zoom in on that, the straighter the line gets. And I'm like, okay, that's good, because if that line's pretty straight, wouldn't a tangent slope be about the same as an average slope around here? Okay, but again, are these values that I'm looking at 4 to 4.05 big changes or little changes? They look big on the graph, but numerically down here, they're pretty what? So the smaller and smaller and smaller I can make this, or the more and more I can even zoom in on this.
So you found an average.
Yeah, the one we had and the one that's really pretty close to it. We just picked one. I just floated this line, point right up and down the line like that, kiddo.
Yeah.
And those are the points that I picked really close to each other, and that gave me a really good idea what the instantaneous slope was going to be around that.
So you just randomly took those points.
Well, the first one I knew because they wanted to know what the slope at 4 was going to be. So to get that value, I plugged 4 in for x, and this is the y value picked out. And then I just drug on that line after I zoomed in. This is as close as it would let me get, because I can't move this point right now. So that's as close as they're going to let me get to it, okay? So within 1/1000th change on the x, what's happened? Okay? Are you good on that?
Yeah.
Okay, so let's take a look where we're at. So what did we end up with slope-wise there? About how much?
22.9.
Who's got a calculator handy right now? I'm just curious. Well, I'm gonna tell you how close we were. Type this in your calculator for me. Do the natural log of 4. Do we have a calculator handy? Natural log of 4. Got that number?
Natural log of 4, okay.
Now times that by, ooh, we're gonna be off a little bit, aren't we? No, I take that back. Natural log of 2.3. My bad. Natural log of 2.3 times 27.9841. Yep. What's that number?
23.208.
So pretty close.
Yeah.
We were 22.9. We're pretty darn close. 23.08 was actual. Okay. All right. So let's see where we're at here. Let's see. Was that all on that page right there, guys? So I think, yeah, let's call it good for today right here. I'm gonna pick the rest of this up tomorrow.